So let me know when I have control. Okay. It's a pleasure to be here to talk about CITRIS. I know we have both newcomers in the audience who are hearing about this grand vision for the first time, as well as a bunch of folks who've been here before. So I'm going to spend 10 minutes of my 40 giving you a grand overview, and then 30 minutes telling you the update from the last 6 months. So that's the plan. So I'll start with the overview of CITRIS as a whole. One of the things that happened in the last 6 months was a sensor day. There were over 100 people, standing room only, all day coming to a seminar and all the work done on sensors just about 1 month ago, and I'm going to give you an overview of the talks that were presented there. I will then choose a few of those new ideas to highlight and give you some more details on, and those are particular ideas that have come up in the last 6 months or about that recently to highlight. And then I will give you a very brief overview of the day's talks. So here is the overview of how CITRIS got put together when we had the opportunity to think about much larger problems than we normally did. Within EECS, we knew that there was all this exciting new technology coming out, so we went to talk to our friends in, for example, transportation engineering, in civil engineering, and all sorts of other areas, and we said, if you had all the information technology that you could imagine in your wildest dreams, think about science fiction, what would you do to completely change your field? And we brainstormed with all these different people, and we came up with a common systems architecture. And we identified 6 application areas in that initial work. And I'll just give you a brief tour of them. The first one was energy. This was even before the California energy crisis. We talked to our colleagues in the Department of Energy, and they said, well, if you look at the office buildings in the US, they consume about 1/3 of the energy in the United States, and half of that's wasted. We know that. They're misheated, miscooled, mislit. And if we could only put sensors in every room, in every office building, we could save 1/2 of 1/3, that's a large amount, 1/6 of all the energy in the United States. Well, why don't you do that? And the answer was the sensors were too expensive. Well, that's a problem that we set out to solve. Then the California energy crisis hit, and we realized we had a lot more opportunities. And I'll tell you about some of those that we've been pursuing. The second one was disaster response. That initially meant earthquakes, of which we have a lot, alas, in California. And we have one of the nation's largest earthquake engineering centers here. They were natural partners to talk to. And then 9/11 happened, and we realized we had a much larger agenda, and I'll tell you about some of the other kinds of disaster response we've worked on since then. In the case of education, we were opening a new university to deal with a tidal wave of students in the state, UC Merced. We went to them and said, would you like to have an online education? Would you like to somehow be able to take Berkeley's world-class, well-established curriculum along with the curricula of our other partner campuses and start your university that way? And we've been trying to figure out how to do that. Healthcare, environmental engineering, transportation engineering, you can imagine sensor uses in all of those. In healthcare, it was, again, emergency kind of things that caught our attention first. Since then, as Rujna mentioned, elderly care has become important. And as we've realized from talking to our European partners, it's even more pressing there. Environmental monitoring, where does all the water go in California? There's a lot of interesting questions about how to do that more effectively, how to use fertilizers more effectively. And in transportation planning, anybody who's driven to the campus knows that we have traffic jams, and there are a lot of ways that you can improve it. In fact, if you drove here this morning, you probably drove over one of our test beds, and I'll tell you about that. So I said that we talked to all these people, and we brainstormed, and we came up with a common systems architecture. Sort of amazing that all those different areas came up with it. So what did that systems architecture contain? It had, so small you can't see it, there it is, MEM sensors at the very bottom that you can measure anything, anywhere, and communicate wirelessly, and I'll give you a brief tour of that. Once you have those small little devices, the question is, how do you put them together into a network so you can measure things, and which could be environmental or building or disaster response, and I'll talk about that. And once you've collected that information, how do I make it globally available and secure so that people anywhere can use it in an appropriate way? So let me give you now a little tour through all these things. And I'll start at the bottom. I'll start with the technology. So when we began doing these experiments in February 2000, that's what a sensor looked like. There's a penny sitting next to it. So that had temperature, pressure, humidity, a few other things on it, a small computer, a radio, an antenna, and it could broadcast information. And we did experiments that way. A year later, it looked like that. This is one of the benefits of Moore's law. You get not just smaller and faster and cheaper, you get smaller. And so that's what the packaging looked like about a year later. A few months later, it looked like that, got even smaller. This is what it looked like in February 2002. This is not quite as much functionality as that. There's a laser communicator and a temperature sensor. This is what it looked like in February 2003. As you can imagine, putting these anywhere. So what is the ultimate? So this is what we have in the do I have a laser pointer here? Yeah. This is what we have in the laboratory. We're still doing experiments out in the field with things that look like that. There's this natural transition of technology. What will all this eventually look like? Well, there's the packaging. Those are RFID packages. Now that's oops, let me back up. Sorry. That D here is the D on the penny right there. And these are what the packages will ultimately look like. So imagine in those little packages you could have computation, sensing, and communication, and they were cheap enough you could put them anywhere. What would that mean? Well, it gets a lot of people excited, scared, all sorts of things, right? So that's the underlying technology. So in addition to making these things small, you have to get them to where they belong. So we have work going on in mobile sensors. This walks, where actually it does push-ups. There's a solar cell. The solar cell produces enough electricity to cause these comb drives to work, to push these legs up and down, and it does push-ups as long as there's a light shining on it, and if we were to build the legs differently, it would actually walk. And in addition to walking, you can imagine making them fly, and this has wings, which beat at about 50 hertz, which is the same speed as a fly, and it does get enough lift to get off the ground now. It's not very easy to control, mind you, but this is you can imagine these throwing them out of airplanes and they'd fly to where they want to go. So these are the sorts of things, this will not happen soon that you can throw them out of airplanes, but this is the technology we have to imagine and plan for. So now let me work one way up in that technology chart and talk about the uses we put them to in a small scale. So in the 1994 Loma Prieta earthquake in Southern California, a lot of buildings of this sort fell down because they weren't very strong at the bottom. So in our Earthquake Engineering Center, people rebuilt them on a shaking table, shook them, and measured them to see how they would have to be retrofitted to make them safer. And that was done with old sensors and with our sensors, and we came along for a factor of about 100 cheaper. And now, it's so cheap, in fact, you could imagine requiring them in all buildings. We also did predictions of ground failure. This is a port, Tokachi Port in Hokkaido, Japan, which is mud flats, the same kind of mud that's all around the San Francisco Bay. When it shakes, it turns into water and all the buildings fall down. And so in this case, it was abandoned land. They dug holes in it, put in dynamite, and blew it up in a simulated earthquake and measured it with our sensors. And now there's studies going on to say, can you predict ground failure and can you predict how to retrofit it by pumping in concrete at the right places? In addition to that experiment, this is a centrifuge at UC Davis where people put dirt and of various kinds and they spin it around so you get about 80 Gs of force, and you can then do sort of mini earthquake simulations inside this piece of ground at a high gravity rate. And with sensors in there, you can predict when ground will fail. So after 9/11, the city of Chicago responded very rapidly and passed a new ordinance requiring all owners of buildings higher than 8 stories to turn in CAD plans for their buildings. Because one of the problems in the World Trade Center is that nobody knew what it looked like on the inside fast enough in the fire department to respond. Then they came to us and we began a relationship to say, how do we use all this information? How do we how do we let the firefighters actually use that information? And so here is a prototype that we built of a heads-up display showing information to the firefighter as he or she walks around inside a building. This is networked to a whole bunch of sensors that show where is the person inside the building, what is the oxygen level, where's the heat in case there are occupancy sensors, is there somebody in the next room, is it worth going in there? And that work is ongoing now with the city of Berkeley. We put these sensors into duck burrows on Great Duck Island off the coast of Maine over a long, cold, rainy season when the biologists didn't want to go there. It monitored the life habits of these actually storm petrels and uploaded the data to the internet, and biologists all around the world could then study the migrational patterns of these birds. And since then, a lot of other biologists have come to us, and I'll tell you about some of those. So similarly, there's an old set of sensors out monitoring the surface currents on Monterey Bay. We're interested in replacing those in collaboration with Monterey Bay Aquarium. Groundwater monitoring done by UC Davis, using sensors to measure the groundwater on the surface, come up with a model so you know where it goes eventually in all of California. Every year, there's a course taught, ME 221, where the students come partly from mechanical engineering, partly from the business school. They're given a box full of sensors, and they're said, design a product and take it to market in one semester. And then there's a contest at the end to see who has the best product. Here's one sample product which actually won a prize in a contest between Berkeley and Stanford in a business school contest. It's called EstroSense. And it measures a woman's estrogen levels and automatically gives that readout, and it's used for medical applications. And I'm not sure if it's got startup capital yet to produce, but it did win this contest. So, and finally, people can wear sensors and walk around in all sorts of places that other people can't go. So, for example, this person, this actor, wore cameras, microphone, other things, and walked around in interesting places like museums and fabrication laboratories, and she was connected over the internet to school children in Oakland. And those children could then all watch where she was going and communicate with her and vote as to where they wanted her to go next. And so this was sort of a way of making education and access to remote places available. So just to repeat then, we have stuff that's very small, all these sensors. We have sensor networks that connect them all together. And then, you'll hear more about this during the talk, there's the making all that information widely available around the globe to people who need it in a reliable fashion. And that's sort of the grand tour. So, actually, are there any questions about the grand tour before I go on to the next part? It's a good place to have a quick break. I'm sure many of you have heard this grand tour before. Okay. So, Ruzhna mentioned that we have a web page. Let me just give you one picture of the web page. How do you possibly keep track of all this work? Well, the answer is you need a matrix. I like matrices. And so, in particular, there's a project matrix which describes all the work going on in CITRIS that you can find on our web page. And at the top, there we go, you have there's one column for each of our application areas: energy, education, healthcare, transportation. And for each row, there's some technology that we're working on, be it sensors or algorithms or human-centered computing or software infrastructure. And at the intersection of any particular point in the matrix, you can ask, well, which work in optoelectronics is being applied to environmental monitoring? And you can click on that, and you can get a list of all the projects there. So that is the way we try to keep track of all of this stuff, because there's a lot of it, 200 faculty and a large number of projects. Okay. So finally, now I go on to what's happened in the last 6 months. And I'm going to give you a quick tour of Sensor Day, which was a month ago, and it was held here. There were 20 faculty talks given during the course of a day covering all these different aspects of sensor net research. So people talked about the systems work, the applications, legal and social issues, which you'll hear about more today, and theory and modeling. And all sorts of different departments were represented, and they were all mixed up. So everybody had to listen to everybody else, and it was a lot of fun. I'd like to give you a list of the participants, but there were so many, they were all standing. We couldn't even get a list around to keep track of who they all were. Let's just say it was a very popular event. There's a partial list of the people who were attending. And in fact, there's a follow-up meeting today, which I'll tell you a little bit more about, the TinyOS Technology Exchange, in which we actually now have seats for 120 people. At least that's who registered. So let me go through these one at a time and give you a summary of what was done. So the legal and social issues I'll defer, because you'll actually have a talk by Deirdre Mulligan of the law school on that topic later today. So here were the talks I'm going to summarize on the systems issues of sensor nets. Jan Rabai talked about low power sensor nodes. Paul Wright talked about using those in an energy scavenging environment, so you don't need batteries anymore. And then David Culler talked about TinyOS, the operating system. In addition to that, Chris Piester talked about smart dust and microrobotics, but I've already shown you all his pictures, so I won't talk about that again. And Joe Hellerstein and Mike Frampton talked about what do you do with all the data that you collect from all these? And you'll hear a talk on that later today, so again, I'll defer that. And just summarize the first three, give you brief summaries of those first three. So Jan Rabai talked about PicoRadio, and this project is motivated by the fact that the bottleneck to making sensor networks work is the amount of energy it costs to run the radio. Computing is cheap, memory is cheap, but communication, sending stuff is expensive. So how do you build a radio that uses the least power possible? And the original goal was 100 microwatts. Why 100 microwatts? Because if you do the arithmetic of a solar cell, how much energy it can produce, or how much energy you produce from just people jumping up and down on the floor, and how much that makes this building shake, how much energy can you get out of that? And the answer is, if you have a 100 microwatt radio, and you have this kind of light level, then this is how often you can run the radio. Or if you have something vibrating, and I'll tell you how much things vibrate, this is how often you can run it. So the idea here is, in a bright light, you can communicate all the time. You've got lots and lots of power. If you're sitting in the inside under a bright lamp, you can communicate 10% of the time. That tells you that there's a certain delay in communication. It's good for some applications, not for others. But if you're only measuring the temperature, it's perfectly all right just to update the temperature every 50 seconds. Who cares? That's more than enough. So that's what this kind of research is about. So the original goal was 100 microwatts. But since then, we've realized that if we could only make that radio even smaller, we'd have a whole lot more applications possible. So in particular, imagine that the radio is small enough you could put this stuff in paint and just paint it on surfaces, paint it onto airplane wings, paint it onto buildings. You could make smart surfaces that could even be more useful, but you need to get a lot lower than 100 microwatts, and the goal is 10 microwatts. And there are currently two different devices in fabrication, 200 microwatts and 50 microwatts, as we work our way down to the ultimate goal of 10. Now, at that point, the way you do communication is not by tuning a receiver to the right frequency. It doesn't work that way anymore. You have to use completely different schemes, and so you're going to put in a lot of random radios that send at random frequencies and hope that statistically the message gets through. So it's a completely different style of doing communication. So this has been used, as I said, to do energy scavenging. This is work of Jan Rabai, whose work I just described, along with Paul Wright and David Culler. And the goal then is to take those devices and make them small enough that you can just glue them to the wall. And I have one in my briefcase, which I forgot. Paul gave it to you this morning, so it's not still a little bit big. This was stuck on some stairs across the street in Hearst Mine and in Northgate Hall. People walked up and down the stairs for a while, and that was sufficient to make a little piezoelectric lever in this thing shake to produce enough electricity to run the radio. And so the goal here, this is funded by the California Energy Commission. They're very interested in this because they want this to be small enough that they can require every home in California, perhaps eventually, to have this, so that houses can control themselves. For that to happen, it has to be very, very cheap. We actually did a demo not too long ago, less than a month, to the California Energy Commission of these sensors being powered by vibrations on wooden steps. And indeed, we've done our homework to make sure that our other members of the assembly know about this work too. So let me tell you where the vibrations come from. You have to do some basic mechanical engineering to find out where the energy comes from in a home. And here are a whole bunch of things that are in a typical home. Here's how much they shake. And you can see there's a great deal of difference. So but if you have a microwave oven, that is more than enough to collect enough energy, store it in a capacitor. I should take this off. This thing has big capacitors in it to save the energy over a period of time and then send it. And then you can use the radio. And so here's the prototype that was used for the California Energy demonstration. It has a little piezoelectric power generator. When this shakes, this little lever bounces up and down. It stores the energy in capacitors, and then eventually that's connected to a sensor, which then goes out over the radio. And this is still a little bit on the big size, so it took 3 people running for 40 minutes to charge up the capacitor. And at that point, we could send 2 temperature readings. Okay, so that's a little bit of an early demo, but the point is it's all on the right technology track, and it'll scale quite well. Right? So the point is there is a prototype that works. Okay, let me move on to TinyOS. This is work of a whole bunch of people. This is a big success. This is the operating system that runs on this sensor and many other ones. And there's a huge amount of interest in it. There have been 10,000 downloads from SourceForge. There's many, many companies who are interested. There are 40 people who download this stuff a day. Lots of press. You can go to their webpage and read all the press in these different magazines. And today, over in the Wozniak Lounge, there are 120 people, I'll give the list of them on the next page, who are having all sorts of workshops on the technology, on which is what the hardware looks like, on synchronization, but also on more high-level issues such as how to support the large community that's working on it and how to interface with the networking industry and who owns this intellectual property. So there's a list of the people who are signed up and are attending this meeting. You can see there's a whole bunch of companies over on this side, large and small, national labs, and a whole bunch of universities that are using this. There are a bunch of emerging standards in this area too. 802.xx is something called Zigbee. So I have to admit you have to ask David Culler about it. So this is far enough along that people are trying to come up with standards that are industry-wide to be able to use this. And that's important if, for example, the California Energy Commission is going to want to require it. You need standards. Okay, so let me move on to the application side of things. And I'm going to talk about sensors in trees, sensors in buildings, sensors in fires, and sensors on bridges. And there are a whole bunch of other sensors, too. These are projects that are quite new, so I'm going to highlight them separately. So right now, I'm just going to tell you about the first ones. So this is work by Todd Dawson, who's a professor in microbiology, joint work with David Culler. His goal is to understand where all the water goes on the planet. And in particular, what role do trees play in the water? It turns out that 2/3 of the water in the planet every day gets recycled through trees. And people are trying to understand what effect does that have on climate. And locally, that means fog. It turns out that in some parts of the world, and not so much in California, but in some parts of the world, the entire source of water is fog landing in trees and dripping on the ground. There is no other source of water. And in the coast of California, it also has a big impact on what the local climate is. And so what he has done is put sensors in trees. So, and this has actually been done in the Berkeley Botanical Gardens. He's doing a test deployment there. And so at various heights above the ground, 5 meters, 10 meters, 15 meters, somebody goes up and puts 4 sensors around the tree that measure temperature, pressure, and humidity. And the data that's collected looks like this. Here's some sample data, temperature versus time. And so very briefly, what does this mean to a biologist? There are 5 readings here. Each one of those readings is at a different height along the tree. The sun came up here. It was very cold, middle of the night. Then the sun comes up, and what this means is that different parts of the tree get hot at different rates. There's a big temperature differential between the top of the tree and the bottom. That pushes an enormous amount of water, much more than simple capillary action would predict. And so from this temperature differential, they can understand where the water goes. Okay, so let me move on to sensors in buildings. This is work of Ed Ahrens, who's a professor in the School of Architecture, and in Paul Wright and various other people. And the goal is, as before, to save energy. And from our colleagues in the Department of Energy, you can identify that up to 1/3 of U.S. energy is wasted in misheated buildings and so on and so forth. So the question is, what do you do about that? They know that if they could just put sensors everywhere, they could fix this problem. But if you use traditional technology, all the cost is having a person go into a room and string the wires so that there's power to the sensor and communication. If you make the wires go away, the cost goes from, well, at a university, putting this thing on the wall costs $1,000. Maybe in private industry, it's $500. Make it go down to $5 or $1. That would be possible. At that point, you can have individual local controls of power and save a lot. And I think I mentioned this before, the California Energy Commission goal is to reduce the cost of an entire setup for an average house in California to $20. That is a thermostat, appliances, and a wireless network to go out to, eventually, the state so that you can get price signals. Has the price of electricity gone up? Are we about to have a blackout? How can you adjust to that? And the idea here is to enable demand response pricing, a real market. If the price goes up, people are going to use less. And so there was a big demonstration on September 16th, 2003, where many people from the state attended, from the California Energy Commission, and all of these different technologies were demonstrated. As I said, it still has to scale down, but it was demonstrated and shown to be real. Let me move on to an outdoor application. Seismic and wildfire monitoring. It's done by Steve Glazer in civil engineering. He's putting sensors into holes right out by the new CITRIS building so we can monitor the Hayward Fault, which it's built right next to. But instead of talking about that, I'll talk about dropping them into fires. So this is work where, so there are a lot of wildfires in California. It turns out that one of the problems is when they start burning, people don't know which way it's going to burn. And you'd think you could just look out of a helicopter and figure that out, but it depends a lot on what's happening on the ground, on local weather information on the ground. And so in his experiments, he's designing sensors with weather boards, global positioning systems, and radio. They're dropped out of helicopters along a fire front. The helicopter is also taking pictures and doing real-time mapping of the ground. The data is uplinked into a real-time burn model to try to predict which way the fire is going to burn. And then that will in turn eventually, this doesn't work yet, be fed back to the firefighters on the ground through some geographic information system to say, you should put your time here or you should get out of there because it's about to burn up. So the hardware and software design is partially complete, and grad students, these are grad students, have been certified to go out and do controlled burns. So that's, not now, it's raining, but I mean, during the right season, they'll go out and do controlled burns. So yeah, you need the right graduate students for this. So this is Golden Gate Bridge monitoring. This is joint work with Greg Fenves, David Culler, and myself. It turns out that the middle of the Golden Gate Bridge can shake back and forth 10 meters in a high wind. They like to get people off the bridge when that happens. It's okay, they think, it's not going to break or anything, but they'd like to have some monitors on there, accelerometers, to detect damage. And this is a very different, harder application than the previous ones because you need very high accuracy, low jitter, high resolution to be able to integrate acceleration and actually get motion. And so, for example, the downhole monitors that Steve Glazer is using to measure small shaking of the ground cost $4,000. That's not yet, large scale. So we designed our own board where it has 2 kinds of accelerometers on it, cheap, inaccurate ones, and expensive, more accurate ones. We're trying to see exactly what we need to deploy in order to do this application. And here's pictures of lots of happy graduate students climbing to the top of the Golden Gate Bridge and looking down and trying not to get too scared. We're collecting data. And the data is not quite good enough yet, but we're working on it. So there's a whole bunch of talks on theory of sensor nets, because once these things get big enough, once you start deploying thousands or millions, then you start to raise statistical questions about what's the right way to design it. And so Michael Jordan spoke about how do you figure out where they all are after you drop them on the ground? What sort of techniques can you use? And other folks talked about scaling. I'll give a very brief tour here. And Sanjay Govinji, who's sitting over there, also talked about a certain aspect of theory, but he will be speaking right after me, so I won't tell you too much about him. So Michael Jordan asked the question, suppose that I have a whole bunch of base stations on the ground, and then I just drop a lot more sensors. How do I figure out where the new ones are, depending on where the old ones are? How do I actually do that mathematical problem? There are two standard techniques. Ranging, you just sort of try to measure how strong is a signal compared to my neighbors. That doesn't work because there's too much local interference. The signal doesn't really tell you about distance. And triangulation has the same problem. So he's using a machine learning approach instead. What you do is you make up a whole bunch of regions which cover the area. And what you'd like to do is decide, is each sensor in each region? And if you decided it's in regions 1, 2, 3, and not 4, 5, and 6, that pretty well localizes it. So what you do is you compute a whole bunch of nonlinear functions of the signals that come out of the sensors, and then use a very general machine learning technique called support vector machines to try to learn what features, learn rules to figure out where things are located. Simulations are very promising, and we're now going to do experiments with real motes. The trouble with the reason you have to do this is because when you put these things out in the field and there's a little obstacle in the way, everything becomes so nonlinear, standard techniques don't work. And in addition to that, there's a large new grant from the National Science Foundation where a whole bunch of faculty are asking scaling questions. And I'm not going to tell you all about this. So one scaling question people ask is, if I drop a whole bunch of sensors randomly in a field, and each one has a probability of communicating with its nearest neighbors, how many do I need so that everybody's connected to everybody else? That turns into a mathematical question from percolation theory. There's also questions about, well, information theory tells you how to do optimal communication if you want to lose as few bits as possible. But now, how does that apply here when we have limits on power, limits on accuracy, when nearby sensors are measuring about the same thing? How does information theory change? Are there new lower bounds on how well you can do? The answer is yes, and that's also part of this work. Okay, so that was an overview of Sensor Day, very quickly. How am I doing on time? Okay, very good. So now I'm going to pick a few new research directions that have come up just in the last 6 months and tell you about them in a little bit more detail. And here they are. Eric Brewer talking about information technology for the third world. That project was funded about a year ago, but some things have happened since then, so I want to tell you about it. Alice Agogino has started working on lighting and medical personalization. As I said, you drove over Praveen Varaya's sensor network on the way here if you drove up Hearst, so that's new in the last 6 months. Annalise Saxenian is the new dean of the School of Information Management and Systems, and she has a project on the impact of RFID tags on privacy, which is pretty interesting. George Akerlof, who's one of our Nobelists in economics, has opened a new laboratory to do experimental social sciences, which we're supporting with money. And I'll also give you a little update on the online education activities. So this is a question about how does information technology apply to the third world, where most people earn less than $2,000 a year and are not going to buy laptops or the kinds of things we usually do. These people have very little education, their markets are local and disorganized, but they spend a lot of money on technology. One of the poorest villages in India, 85% of the people have TVs, 21% of them have cell phones, perhaps Nokia cell phones, who knows. And the question is, what role does technology play in these societies? And the question is, this is not a question about charity, it's a question of what business models make sense so that these people, you can produce products that these people will buy and will make their lives better and that can be afforded to be done economically. So let me give you some examples to show that this is very much possible. There are actually a lot of stories, but here's several success stories. So this, in the first one, a sensor network, an old-fashioned, expensive sensor network, was laid down in West Africa to measure water levels. And based on those water levels, people could figure out what was the right time to spray a certain kind of pesticide to get rid of certain kinds of flies that carried a fever, dengue fever. They eradicated dengue fever. There's 30 million people who can now live on this land they couldn't live on before. It's 100,000 square miles of farmland, and that can feed another 17 million people. So that was a sensor network application that was an amazing success. And we're planning to extend that into Central America, where they have similar problems. Another one, which was an economic success, was the Sri Lankan rice market. So it turns out that the way the rice market works there is that you have rural farmers out in Sri Lanka. They take their rice to middlemen. The middleman pays them some money, and then the middleman sells it in downtown Colombo, the capital. Well, what they did in this experiment is they gave wireless devices to all the farmers. So the farmers could find out what the price really was. They quickly discovered the middleman was cheating them out of half their money. And they said, no, we're going to pay the right price. And they doubled their incomes and got rid of the middleman. And so that was an enormous economic benefit just by having enough information to make the market efficient. And perhaps the most famous example, and this is a partner of ours, is the Grameen Bank in Bangladesh, who invented the idea of micro-lending, mostly to women for businesses. And they've loaned an enormous amount of money profitably with a high recovery rate, and it has funded their national cell phone network. So these are sort of the examples that we would like to be able to emulate, and you can imagine all sorts of other ones. And we have a list, and a long list of partners who want to help us there. So what are the research issues? The first thing is it has to be really cheap, and it has to be very low cost, and it has to be very low power, because we're not going to have wall outlets in all these little rural villages. The other thing is that you're not going to have network coverage that goes everywhere. So you're going to have some sort of method to have intermittent networking so that the data is stored locally, and then eventually, maybe when the bus goes through the village once on a daily basis, all the information gets downloaded at that time and stored in some persistent data center where, in some town where you have persistent storage and electricity. The other issue is literacy, because most of these users, even though they have money and they're going to spend it and buy this stuff, are going to be illiterate. And that means the user interfaces are going to have to assume that. And they're also going to speak a whole bunch of different languages. So it's going to be an interesting question of perhaps it's speech recognition, perhaps it's certain kind of icons, and these are the research issues here. So this is very exciting to a lot of people. We have a lot of partners. In fact, HP has established a lab in India. They think this is a real market too. And a whole bunch of social scientists here. We are planning our first deployment in India in a rural village in 2005, and we're going through a long list of possibilities about a second deployment in the next year, which might be a fever eradication project in Central America. Okay, let me go on to Alice Agogino's work, which is on lighting and medical personalization. This is again motivated by the saving energy business. So it turns out that if you just think about light, forget the heating and air conditioning, even light, if you just did that right, you could save 12% of all the energy usage in the US. So what are the problems with the current controls? Forget the fact that they're too expensive. It's that they're not customized to the occupants. One person likes it bright, another one likes it dark. It doesn't depend on the time of day. If it's cloudy out or if it's bright out, you might want to use different amounts of internal lighting. And so how do you take all that into account to design a lighting system that saves energy and makes people happy? And so the research goal is to collect enough information so that you can, which is going to come from detailed user surveys, where you can identify the variables that make people happy and not, come up with a big mathematical model of all this using something called influence diagrams, and then do a probabilistic optimization so that for each workplace, they will get their own particular algorithm for controlling the lighting that is tuned to their particular inhabitants. So Praveen Varaya has been, now I'm going to move on to traffic monitoring, has been associated with the PATH project for many years. This is a big joint project between California Department of Transportation and University of California to automate highways, to use better information systems on highways. And the observation is that if you only knew where the cars were, you could control street lights better. That's pretty obviously red and green. You could control on-ramps better. You can control public transportation. And you can run a big mathematical model that says, what would you save? And the answer is 15 minutes per commuter per day. And if you multiply by how many commuters there are, this is in the Bay Area, 15 minutes per commuter per day times the number of commuters times how much they make, you save billions of dollars every year. And so the question is, can this be made feasible using all this new sensor technology? What are the requirements for technology? It has to be really cheap to install, because right now there are loop detectors under the highways. We've been driving over them for decades. They last about 10 years. They have to close the whole freeway, and you have this big machine go dig up the concrete and put it under there. Can we avoid that? Can we just have them stamped out onto the concrete? And those little round bumps that you drive over, don't like. It has to be cheap to maintain. Can't have people go out and change the batteries. And it has to have a low delay in getting you the information. If you're going to run a street light, it has to be about 1/10 of a second communication rate. And so here's some examples from the corner of Hearst and Euclid, where these sensors are out there running. There's both microphone sensors and there's magnetometers. And there's a lot of interesting signal processing questions about which data is more reliable in order to detect cars going by. This, for example, was the wind blowing, and you got a sort of a false alarm there that a car went by. The last time they did this experiment, they managed to correctly identify 212 out of 213 cars. So it is pretty accurate, but velocity is still not that accurate. So they're still thinking, how do they do better signal processing, and how do they compare network protocols to get the delay down to 1/10 of a second? Okay. This is a privacy project, so it has a different flavor, and it's just starting. It's Annalise Aksinian and someone who's a private researcher, Ross Stapleton Gray, and they call it the Sorting Door Project. So imagine that you have a door which has RFID tag readers all around it, and people walk through it. And you put a whole bunch of these around, say, a campus, and you collect all that information about what every RFID tag, every person who walks through the door is. What books are they reading? What clothes are they wearing? What would you do with all that information? And how are they going to react to it when you actually collect that information? So the idea is to build these doors, which could be real doors or just something around offices, network them to something called an identification engine. The identification engine uses something which is being built by a public company called an object name service, which is a repository for what all the RFID tags mean. And to other databases, and say, how much information can I deduce from somebody having a certain book in their pocket, from all those other interesting things that might be known about you? So one of the research questions is, well, how effective are these RFID readers? How much information can I actually get out? How aware are people of these things? I mean, for example, the door could announce that, hey, how come you're reading, you happen to be reading a book because it has this RFID tag in the library book that you got out. That'd be interesting. How would a person react if you suddenly knew they had a book in their backpack as you walk past? What behavioral patterns can be extracted? Is there a tipping point where suddenly people get very uncomfortable about this? If this sounds like 5 minutes, thank you. If this sounds like something that someone from the CIA thought of, you're right. This gentleman used to work for the CIA, but then he worked for the University of California. Okay, we opened the Social Sciences Experimental Lab, which is run by our Nobel Prize winner George Akerlof and a bunch of other people from the business school. And this is reflecting a change in the way social scientists do business. In fact, there have been the last Nobel Prize, next to last Nobel Prize, was for people who do hard, controlled laboratory experiments to measure how people make economic decisions. And the idea is, how do we support that research at Berkeley? And they've opened a lab with a shared facility, space, and computers for people to do these experiments. And they give grants to support people doing this. And the support comes from a number of our partners. And let me just say that their plans are to open this to industrial partners who also want to do experiments in how people make decisions about how their products are purchased. Education, I will be quicker now. CS4 is a new undergraduate course going to replace our old one, which is for programming for engineers. It's going to be Java-based. It's going to be based on UC-WISE, which is our online education system. It's going to be available to UC Merced and elsewhere. And so I'm looking forward to seeing if this will be a good programming language to teach at UC Merced. Richard Newton and Paul Wright also just created a new partnership with Taiwan National Chung Tao University, where we're going to exchange people, students, and also online education through the new Distance Learning Center in the new CITRIS building. And so this is sort of an interesting experiment in the idea that people talk about outsourcing and globalization. Well, it's happening to education too, and we're sort of trying to see what that all means. So, and I could get, let's see, a very short preview of today's talks. How much, do I have enough time to do that? 3 minutes, okay. So Sanjay will talk about computer-aided design for MEMS, whose goal is to provide a SPICE-like environment for MEMS design, which doesn't exist right now. Jeff Bokor is going to talk about his recent great success, which was in the press, about actually integrating nanotechnology in silicon, gluing carbon nanotubes to silicon, which was never done before, which is a prerequisite to making nanotechnology commercial. Ali Shakouri will talk about putting little micro refrigerators on chips by exploiting the lattice properties of the silicon. This is going to be necessary to get smaller, denser chips. Chao Chang will talk about China's internet revolution. There are 78 million internet users in China. It's changing everything about the way that life works in the Chinese society, and he's going to give us a survey of what's going on there. Doug Tigar will talk about the security and privacy research going on. A number of large new grants have come in. Jonathan Heritage will talk about optical networking, making the entire network optical, including the switching. Michael Franklin will talk about how to deal with all of the huge amounts of data that are coming from Sensor Net. Deirdre Mulligan from the law school will talk about privacy issues and whether the current legal system makes any sense at all in a world where all this information is being collected. Ed Lee will talk about a system which has already been demonstrated, which is an automatic pilot that kicks in if somebody tries to aim an airplane at something they shouldn't be aiming the airplane at. And finally, Oliver Statt will talk about how to visualize all this data that's coming out of sensor nets. Thank you very much.